Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to talk about the images as well as the optical instruments, such as your lenses, such as microscopes, telescopes, and everything else that involves with the redirection of light. So before we get started, please consider subscribing as well as liking the video, and also please check the link in the description for the notes throughout this entire discussion. So in here, we will actually start to discuss about the idea of images. And so for you to understand about images, you need to know about the reflection as well as refraction, because these two phenomena is going to be discussed throughout this entire discussion. So let's start by actually defining what is a real image as well as a virtual image. So if you remember from an object, it will emit, it will scatter some light back at the surroundings, and each of these rays corresponds to the light that is scattered by the object, which is pretty much containing the information of the object in itself. So the idea is that if it all converges into one spot for the light, we call this image as a real image, because it is where most of the light focuses back into a certain point in which it will have the illusion of having the same object, so it is real. But for a virtual image, you would have it to be something like this, in which your rays diverge. So why is it a virtual image? So actually, if you try to take the lines back, what you would have is that there is some form of a image at the backside here. So that's the virtual image. So it is like for the real image, it is as if it is re-emitting the light. But then for a virtual image, what you have is a projection of the rays going back to have that image formed. So the virtual image is just an illusion, while the real is the actual light focusing on that particular point. So this is important for us to discuss within lenses as well as mirrors. But for now, we should start to discuss about the mirror first. So to discuss about mirrors, we'll actually observe this in a much more mathematical form. So if we have a mirror, which is on the x-plane, or y equals to 0, and then you have your point to be at this point here, which is at 0 point P, or D. So the distance from here to here is something which we will call as D, small d. So the question is, where would the reflection be? So technically, all of the light will later hit the mirror, and then because of the loss of reflection, what you have is that there is some reflections for it to create an image. But then the question is, where would the image be? So this is just a sketch of like where the image could be. The theory is that the image would be inside the mirror, in which it is a virtual image. But how do we describe this mathematically? So we could actually do it something like this. So if we have this point and then we have this mirror at the x-axis, you could describe a ray going through to be y equals to mx plus d. So the d here is the y intersection. So if you put x equals to 0, the y is d, which is true, and then you have this m, which corresponds to the gradient. So it's the gradient from here to here. So now with this gradient, we could actually determine what is the angle from here to here. So the gradient in here is pretty much y over x. That's the change of y over the change of x. And if you actually look at this in terms of the angle, we could actually describe this as the change of y over the change of x, meaning that it's the cotangent of theta. Now, because of reflection, what you would have is that the mirror will later reflect the same angle theta, but in the negative direction. So this is negative theta technically. So this is for the real light, this is the incident light, but then for the reflection, what you would have is that the slope is going to be cotangent of negative theta, or the same thing as writing this as negative cotangent theta. So you have your slope to be flipped. So what you would have is that this y equals to negative mx plus a constant c. So also with this, we need to make sure that the reflected light is also starting from our point within the x-axis, or the x-intercept, in which y equals to 0, and they have to be the same. So for the ray to be continuous, it needs to be at the same point. So that means that the position in x as well as the y must be the same. So we could try to determine where is the x-intercept for the incident light first. So at y equals to 0, this must be equal to mx plus d of the particular point. So this is xp. So xp in here is gonna be negative d over m. So if we try to substitute this into the reflected ray, so substituting the value in, what we would get is that the y in here should be 0. No, sorry. Yes. So the y should be 0, which must be equals to the negative m times the negative d over m, which is d plus c. So what the c here is going to be the negative d. So what you get from the reflected light is that y equals to negative mx minus d. So here's something interesting. When you see this equation, it obviously has two different slopes, but the most interesting thing is that even though you change your even though if you change your slope or the angle, the y-intercept of your reflected light is always at negative d, meaning that this is always within a distance of negative d from your x-axis, or pretty much within your mirror. And this light is also imaginary, because the y is always greater than 0. So let's actually talk about, for example, a certain image in which I want to find the reflection across a mirror. So if we have this mirror, and then we have this object, let's state that with an arrow. The easy way for you to describe the image is by taking the rays out. So you could drag this along, and then this will go across. But then for this top layer here, this would be dragged into the mirror until here. And so the reflection is going to go in this way and going this way. So this thing here is your theta. That means this will also be your theta, which also means this is your theta. So this will be the same height as well. So for a mirror, your reflection will also have the same height and the same distance from the mirror. So it is as if that you only flip the x-axis around. So this is a very simple description of mirrors within a straight mirror. But what about if we talk about curved mirrors? So the description is a little bit harder, but we could try to observe one certain example, which is a parabolic mirror. So we'll try to describe this by also using mathematics. So for a curved mirror, let's say a parabolic curve is y equals to ax squared. So it has this form of curve. Now let's assume that all of the light hits the object perpendicular to the mirror. sorry, it is on the same axis as the axial component of your curved mirror. So let's think of a particular point within this entire mirror. Let's say within this particular section. And let's observe this in a much more closer detail, in which it has some form of a slope. So the slope here has a certain angle from the x-axis, which I'll call this as theta. So how do we compute the theta in here? So we could compute the theta by actually taking the tangent. So the tangent of theta is pretty much your dy over dx. So this would basically be your 2ax. So all of these observations that I will be presenting in here will mostly deal when you have positive x, but it also works in the negative x because it is symmetric. So you could do the same computations with negative x values. But anyways, what we saw here is that we figure out what the tangent of theta is, which is 2ax. And so what we could do from this is that we could actually extend this into your normal axis of the plane, because this is the most crucial information that you need to get when you are dealing with the reflection. So if this is theta, we could take the light ray, which is going directly into the mirror, or pretty much in the same axis as the axial axis of your parabola, and this will also form the same angle theta. So a observation of this is pretty much looking at the change of the angles. This is perpendicular, and then this is also perpendicular. So that means that the angle should be the same. So with this, we could actually figure out that there is a reflection with the same angle theta. So that means we figure out what's the slope of this guy. So we should try to figure out what's the slope of the reflection. So the slope of the reflection here, so we will use the 2 theta. So for the slope m, it's going to be the dy over dx. So dy is this part and dx is this part. Or if you draw it for the 2 theta, this is dy, this is dx, and this is 2 theta. So observing this triangle, this is the cotangent of 2 theta. Sorry, this should be negative cotangent of 2 theta. So from here, we could actually try to extend this to write it in terms of our tangent theta. So negative cotangent 2 theta is going to be negative cosine 2 theta over sine 2 theta, which means your cosine 2 theta could be expressed as cosine squared theta minus sine squared theta over 2 sine theta cosine theta negative. So with this equation, we could rewrite them all in terms of tangent theta. So we could divide the top and the bottom by cosine squared theta. So this is going to be negative 1 minus tangent squared theta over 2. So the sine will later cancel out. No, sorry. We divide everything by cosine squared theta, which means this will be tangent theta. Or this is going to be tangent squared theta minus 1 over 2 tangent theta. So your slope, if you actually revert to what tangent of theta is, it's 2ax, meaning that the entire slope is going to be 4a squared x squared minus 1 over 4ax. Now, this is the slope at a particular point, so we'll just denote 1. So this is x1, in which it is where the light hits your parabola. So after this, what we could do is that we will try to express your y equals to mx plus b again. But we will rewrite this in a much more better way. So we could just write this as y minus y1 equals to mx minus x1. So So this is what you get from pretty much linear equations, in which if you know the x-intercept and if you know a particular point within this line as well as the slope, you could figure out the entire equation of your of your linear equation. So if we try to put the slope in as well as the particular value of y, which in here is going to be the ax squared, so this is ax1 squared equals to 4a x1 squared minus 1 over 4ax1 x minus x1. Now, with this, what we could do is that we could try to actually to extend everything out. So this is y equals to 4a squared x1 squared minus 1 over 4ax1. Multiply this by x. So this is your slope. And then you could add it by ax1 squared as well as the slope, multiply that by the point of x1. So this will be minus 4a squared x1 squared minus 1 over 4a. Now here's something that is mind-blowing. If you observe only this part and try to simplify it, you would have ax1 squared minus ax1 squared again plus 1 over 4a. You could cancel out the ax1 squared. So what you would have is this 1 over 4a. So this means if you know the a within your parabolic mirror, you could figure out that there is a certain point in which all lights, which is hitting it at this axis, is going to be focused on. It is always when y equals to 0, when x equals to 0, within the height of 1 over 4a. So the height from here to your focus point is 1 over 4a. So all of the lights will hit this particular point. So this is something interesting. But we could also extend this much more further into the idea of the radius of curvature. So what the radius of curvature exactly is that you could actually make a circle such that your circle is only intersecting it at only one point, but also have the same double derivative. So I will try to derive the equation of the radius of curvature first, so that we could use it for our discussion. So for the radius of curvature, so we could create a circle. It's r squared equals to x minus a squared plus y minus b squared. So this is pretty much a circle with radius r at the point A, point B. So if we take the first derivative with respect to x, let's say, because the radius doesn't change, we know this to equal to 0. And this would equal to 2x minus a. The derivative of x minus a is 1. And we add it by 2y minus b, and then the derivative of y minus b with respect to x is dy over dx. So we could keep on deriving it one more time just to get out the a. So we could get in here 0 equals to 2 plus 2, the derivative of y minus b, it's going to be dy over dx again, times dy over dx, plus y minus b, which is still there, multiply that by the second derivative of y. So this is pretty much just the product rule. So what you get from here is that you could determine what is the y minus b. So this would be negative 1 equals to dy over dx, everything squared, plus y minus b, d squared, y over dx squared. So your y minus b is going to be is gonna equal to -1 minus dy over dx, everything squared, over d squared over dx squared. So this is your y minus b. That means you could also figure out what is your x minus a, because we have this other equation here, in which it's the first derivative of your circle. So let's put it in. So what you could get from your x minus a is going to be this would plus your y minus b dy over dx equals to 0. So your x minus a is going to be the 1 plus dy over dx squared over d squared y over dx squared. Multiply this by dy over dx. So with these two equations, we don't need to know what the a and the b is. So we could use the very first definition of the radius of curvature to figure out what's the r, or your radius, exactly. So if we try to plug your x minus a as well as your y minus b, you get here r squared equals to 1 plus dy over dx squared over d squared y over dx squared, with the dy over dx squared here. And then you could add this with the y minus b squared, which is -1 minus dy over dx squared over d squared over dx squared, everything squared. So this means you get your r squared here to be 1 plus dy over dx squared over d squared y over dx squared. Sorry, so this is squared as well. Squared, multiply this by 1 plus dy over dx squared. Now taking the square root of this, what you observe now is a very interesting equation. R is equal to 1 plus dy over dx squared, everything is raised to the power of 3 over 2, divide that by the d squared y over dx squared. And this is the general rule of radius of curvature. So let's ask about this question. What is the radius of curvature of your mirror? And so we could assume this mirror to be, let's say, circular. So if we try to plug in your y equals to ax squared, your r is going to be 1 plus 2ax, everything squared, over the second derivative of your y, which is 2a. And evaluating this when x equals to 0, what you obtain here is 1 over 2a, which is your radius of curvature. And this is also something interesting. Remember, so let's try to figure out the ratio between your radius of curvature as well as your focus. It turns out that the value in here turns out to be, so radius is 1 over 2a, the focus is 1 over 4a, the ratio is 2. That means that the radius of curvature is 2 times the focal length. So it's a very good approximation when you are talking with a circular mirror. But because of a circular mirror doesn't have the property like a parabolic mirror, you have something which you call as spherical aberration, in which the light couldn't really focus at one particular point. Instead, it is slightly shifted. So finally, we could talk about the concave mirrors or the convex mirrors. But in here, let's talk about the idea of mirrors first. So if you have this mirror, so if I draw this correctly, it should be like this. It has a focal as well as a radius of convergence. No, sorry, radius of curvature, which is located twice the length of your focal length. And you have light, and then you have light. So if the light is going parallel to the screen, it's gonna go through the focal length. This is what we have already observed when we talked about this focus point for a straight ray hitting the parabolic mirror. And when the light hits the focal length, it's going to be reflected parallel. That's the second idea. The third idea, if you have a ray hitting your mirror and it hits the center, it will also reflect at the same angle. That's another fact. And lastly, you could take a line. Sorry, you could take a ray and then hit it towards the radius of curvature, and it will later reflect back without having a change within the angle. So in here, what you have here is that this is your focus point. It's very interesting to see that there is this point in which all of the rays within a certain point goes to. So this is the idea going forward when we are talking about concave convex mirrors. So let's go and discuss about the image within a concave mirror. So in here, so we have discussed about how do we do ray tracing. So now what we could do is that if we have the focus as well as the center point, and let's say if we have a image, let's say it's this arrow, and I want to figure out where would the reflection be. So we could just take lines parallel, and it will later be reflected back like this. So that's your first point. And also, you could just straightaway just take this guy and then go and pass it through the center point. And this will be your reflection. You could also do another method, which is just pulling it towards the center point. No, sorry, towards the focal point. You could pull it and then let it reflect back. You can see here that it is reflected back. It's reflected back at the same point. So from here, if your image is above C, what you have in here is that you have a real image because everything converges into one point. Secondly, it is inverted because you can see the image is upside down. And lastly, it is reduced. The size is getting smaller. So that's what happens when you have a mirror and then you put the image above its radius of curvature. But what if we actually do the same thing, but instead at this point? What will happen to your reflection? So we have the same ray when it passes through when it goes perpendicular to the mirror, and then you could take this ray and pass it through straight away. So there is this location in here, which is gonna be where your image is gonna be at. So a value which is less than, so it's x here. So if you put your object between the focus point and the curvature, and sorry, the radius of curvature, what you have here is a real inverted enlarged image. Now finally, what if we put our object within, so let's take a different color, blue. If we have our image to be less than the focus point, let's say in here, we could take the same ray from the center of the from the radius of curvature, and if you extend it in here, what you have here is that we have a point in here, so it's here. So what we see here is that there is a imaginary, because this is not really the real ray. The real ray goes in this direction. But the focus point that we observe is that there is this imaginary point behind the mirror. So this is why we call it as imaginary. So it's imaginary, but it's upright. And it's also enlarged. So this is the observation that you see for a concave mirror. So concave in here really means that it is going, so if you have your light, it is, the center point is much more further compared that to the edge. So what about a convex? So convex is the opposite, in which the center is much more nearer compared that to the edge. What will happen? So for a convex mirror, you have your radius of curvature to be here. That means that your focal length will be here. So this is what makes things interesting, because if you actually try to observe the image of, let's see here. So if I put my focal length here and then the radius of curvature there, if you have an arrow, if you take the ray tracing, so if you take this light and then take the reflection, it should go in this way. It's something like this. But then if you take it from the radius of curvature, you would see that there's this intersection point here. And this is your image. So this is a imaginary. Upright. But it is also reduced. So this is a very cool property of a convex mirror, in which any image that you put outside of the thing, it will later seem as if that it's much more smaller. So this is why we use convex mirrors when we put it in a junction, because it pretty much contains all of the information of the surrounding images just by making the image much more smaller. So that's something interesting. So now let's try to develop a much more better understanding of mirrors. So we have one thing which we call as the mirror equation, and we'll try to develop the derivation of the mirror equation. So we will define the magnification, and then later we could figure out where is the position of your image is located at. So we will define magnification to be h prime over h. So h prime is the height of the reflected image, and h is the original image. So if we have a concave, it's gonna have its focus and then its radius of curvature. So it will later be reflected like that. So this is h prime and this is h. Now this magnification could be written in terms of your distance, because what we see here is that there is something to do with geometry in here. So if this is the distance from the object to the mirror, you could determine what is this S prime, or the distance of the reflected image. So observing this by only using proportions, you could actually sketch some more ray tracing just to make it much more clearer. What we see here is that this height and this height is being compared, which means that this distance and this distance should also be compared. So it's the S prime over S. But here's something. You need to remember that this is the negative of the S prime over S, because we are dealing with a object in which it has inverse, which has the inverted image. So we put the negative there because it doesn't come from geometry, but it comes from the definition of our S. So we'll define our S to be from the mirror and your S prime to be also from the mirror towards the image. So virtual images will have negative S primes. So anyways, we have got this idea. Now that's only for the magnification, but how do we figure out what's the S primes? This is where the mirror equation comes in. So to develop this idea, we should try to figure out the relation between your distances with the focus. Let's try to think of this. If we see from this image, we have the same angle in here, which means these two guys should have the same, should be similar triangles, but with different proportions. So in here, the height should be h, because you could take the length here. This is h, and then you have the smaller one, which height is h prime. So with that, we could also state that this length from here to here is S prime minus the focus, because it's the length minus the focus. It's only this part, so we are only subtracting a portion of the focus of the reflected image, and in here the total length is gonna be the focus. So this means we could create a equation. H prime over h is your S prime minus f over f. Now we have already determined what is the magnification. It's negative S prime over S, which equals to S prime minus f over f, which means we could develop this much more further. Multiply both sides by SF, you would get minus S prime f equals to S prime S minus SF. Or we could make this much more simpler. Sorry, my bad. So technically this is the magnitude, because we are dealing with geometry. That means that we don't have any negative values. So everything has to do with length. So this is positive. My bad. So with this we could say S prime f plus SF equals to S prime. So divide everything by S prime f. What we get is 1 over S plus 1 over S prime equals to 1 over f. And this is your mirror equation. So here's the fact that we need to use. F in here will later represent a focal length. And so for positive values, this is a concave mirror, but negative means it's a convex mirror. So that's everything to do with mirrors. Now, we want to go into lenses. So lenses also have similar properties, but the way that we'll describe it is much more harder, because it has to do with the refractive index as well as the other things. So instead of dealing with the physics, we will deal with the geometry first. And let's try to figure out about lenses first. So here's a fact that I will give first. If you have a convex lens, it will focus the image. It has a real focus in here. This is real. So this is the real focus. But if you have a diverging lens or a concave lens, you would have it to be diverging. So your image is gonna be like a reflection. It's gonna be here. It's imaginary. So this one will have positive focus, and this one will have negative focus. So I also want to talk about the ray tracing for lenses. So for lenses, oh, let's draw this better. There you go. So for lenses, anything parallel to the lens will gonna be focused at the focus point. And any light that goes through the lens will also stays true. So this is a fact. And also you could actually try to figure out why it works, and there's some logic into it. There's something to do with symmetry. There's also something to do with the focus length again. But in here, we'll just state that this is what it is. So we could do the same idea with ray tracing for images within a lens. So let's have a convex lens. We could take this guy, and then we have a lens here. And let's have the focus to be here. So let's put a image here. Well, technically, I should actually also have the radius of curvature, because it is also a little bit important. So if you have the image here, where would the focused light be after you look at it through the lens? So using ray tracing, you could take a line there, and then whoosh, it goes down. But you could also extend this towards the center to observe that this guy is here. So this is way before our second R. So what we see here is that it has a pretty similar property, in which it's real, it's inverted, and it's scaled down. Yeah, it doesn't look like it, but it is actually scaled down. It's scaled down or reduced. But what if we actually extend this from the radius of curvature towards the focal length? We could do the same extension. But instead, the only difference is the light going through the center of the lens. We see that there's a enlargement within your light. So it's real, it's inverted, but it is enlarged for anything in between the focus as well as the radius of curvature. Finally, if we go with a different color here and put your image within the focus length, what you would have is that this will be a imaginary image. So it's imaginary, but it's upright, and it's also enlarged. So it works very similar to how mirrors work, but instead your real and your imaginary image are flipped. What about for a convex lens? So if you have your image here, it's gonna hit this guy, and then it will try to hit your focus, which is technically here. So it is gonna be scattered outwards. But you could also take your ray and then go and pass it through the center of your lens. You have the image to be another imaginary one here. It's imaginary, it's upright, but it is also reduced. So it's actually the exact same thing as for mirrors, but its position is a little bit swapped. And you could actually do the same idea with the magnification as well as the lens equation. So the magnification is going to be h prime over h, which it turns out to be the same thing, negative s prime over s. But in here, your s prime goes across. So if you have this guy, the length here, this is h prime, this is h, you could take that and then you take that. S prime goes here, and then S goes this way. So it is okay to have it within two different directions. Now, to develop the lens equation, you just need to use geometry again. So let's do that again. Let's just, so if we have this here, and then we have our real image, and then your reflected image here. If you take the line there, and then actually this already works. No, technically I need to make another one. This one goes through the focus, so this is your focus. So what we observe from here is that there is some geometry that is lying within this image. So we see here that the one going like this, which is this part, and let's actually highlight that within a different color. This one must be the same triangle as this one. It's just inverted. So this is h prime and this is h. So everything here is the same. So we could say this is your f, and in here this is your s prime. Now, with this we could actually develop another ratio. S prime over f must equal to h prime over h. Or this is your s prime over s. No, sorry, this is s prime minus f. So it's s prime minus f here. So it's pretty much the same magnitude here. That means it's s prime over s. So if you use the same logic as before, you could multiply both sides. It's s prime minus sf equals to s prime f. And this turns out to be the same thing. 1 over s plus 1 over s prime equals to 1 over f. So the lens equation and the mirror equation are the same thing, but the difference is that for mirrors, the s prime is at the other side, while the s prime in here, for the lens, goes through the lens. So that's an interesting difference between mirrors as well as lenses. But now we should try to understand the physics behind lenses. So if we actually look at the physics, it's pretty simple. So if we have a convex object, so anything past this barrier is n, has refractive index of n, outside is air, so it's 1. And then you have an object here. The question is, where would be the focus of this object? So we could use small angle approximations. So let's just make a line from here to here, and then in here there's this radius of convergence, and the radius of curvature, and then in here we have the focus, which is going to be where the light is going through, and then in here what you have is the you would have this angle here to be theta 1 and the angle here to be theta 2. So this corresponds to the Snell's law. No, sorry, the focus shouldn't be there. It should be much more across there. So this will be your focus. This is your theta 2. And we'll call this gamma, beta, and alpha. And alpha, beta, and gamma are very small. So alpha, beta, gamma are very small. Oh, also theta 1 and theta 2. So let's try to use Snell's law to figure out the relation between theta 1 and theta 2 first. So n1 sine theta 1 must be equal to n2 sine theta 2. But for small angle approximations, you could assume this to be theta 1 equals to n2 theta 2. But n1 is 1 and n2 is just n. Okay, so that's the first relation that we have. But we could also see the relation between theta 1 and some of the angles. So what we see here is that pi minus theta should be pi minus alpha plus beta. Or pretty much this is a relation of a triangle in which the angles should sum up to pi, or 180 degrees. This is the same logic. So we get theta 1 to be alpha plus beta. And this also works for theta 2. Theta 2, so pi minus theta 2 is the same thing as, so it's the same thing as pi minus beta plus theta, so instead let's just write it like this. So pi minus beta plus theta 2 plus gamma should also be pi. So technically this one should also be pi minus theta plus alpha plus beta, because it's just the way that you could derive a relation from the geometry. So you would get the relation here, theta 2 is beta minus gamma. Now, you could substitute the value in, or you could just figure out what's the alpha and the beta and the gamma. Alpha, beta, and gamma are small angles, which means that we could just approximate this by using tangent of alpha, tangent of beta, and tangent of gamma. So what's the tangent of alpha? So if we state this to be our height, h, we could get h over s, s is this distance. The beta is h over r, or the radius of curvature, and gamma is the focus, h over f, or the s prime technically in here. So combining them all together, you would have h over s plus h over r equals to n times h over r minus h over s prime. Now we could collect all of the s primes to the left and then all the r's to the right, cancel out all of the h. You would have 1 over s plus n over s prime equals to n minus 1, 1 over r. So anyways, the 1 in here is technically n1. And the n's in here corresponds to n2. So this works for any type of refractive index. If you have some form of a curvature, you would have this type of relation to figure out where is the light going to be focused at within the lens. So this is the only tool that we need to figure out the focus of any type of lens. So we could try to create a lens, let's say. So we have something like this. So we would have light hitting here, and then it will hit the first barrier, and then it will hit the second barrier. And the question is, where would the focus be? So we could try to solve this straight away. If our image starts from S, from the point S, and it has thickness, let's say T, we could solve it like this. From the first barrier, we would have 1 over S plus n over s prime, the one that we are questioning. No, sorry, it's not really something that we are questioning, but it's where the light is going to be focused at, or pretty much where the object is going to be at. It's going to equal to, we will later have the image to be at s prime prime. So this would equal to n minus 1, 1 over r1. But then on the second barrier, you will use the s prime. So the position of s prime will be probably around there, or maybe even further. So what we could say is that this will be 1 over t minus s prime plus n, no, sorry, so this is n, and then this is 1 over the s prime prime. This should equal to 1 minus n, 1 over r2. Now for very small thickness, so we will assume this to be very small compared that to s prime. This would be n over s prime, negative, plus 1 over s prime prime equals to 1 minus n, 1 over r2. Now, if we add this guy and this guy together, what we would obtain is 1 over s plus 1 over s prime prime, or the actual image that we see from the lens, must to equal to n minus 1 of 1 minus r1 minus 1 over r2, or the difference between the radius of curvature. So this is something which we call as the lensmaker formula. So this s and the s prime prime is something which you know from the lens equation to be 1 over f, or the focus, or the reciprocal of the focus point. It's n minus 1, 1 minus r1 minus 1 over r2. So we have seen how do we actually construct lenses. And so for lensmaker, especially for eyeglass maker, this 1 over f is something which you call as a diopter. So a diopter pretty much tells you about the reciprocal of the focal length. And this is the measurement that is used to actually to fix your eyes. So what glasses are you? I have a +2, which means that it is a convex lens with focal length of 1 over 2. That's the idea. So for lenses, you have something which you call as lens aberration. So a very unfortunate thing about the real world is that your refractive index is not constant. So n is proportional to your frequency. And so with this, there is something which you call as a chromatic aberration, in which the colors doesn't truly focus at one point. Instead, it is scattered. So you would have, let's say, for like fine edges, there is difference of colors. I mean a little bit when you talk about glasses. So that's the first type of aberration. Another one is spherical aberration, because lenses aren't real spheres. So what you have is that there will be some resolution lost when it comes to using lenses. So this is an unfortunate thing about lenses. I also want to talk a little bit about astigmatism. So the way that I understand this is that astigmatism means that you have the lens within your eye to be different within different directions. So it has different curvature, which means that you would have different type of focuses within your eye. So you don't have a truly full resolution image within your brain. So after we have already fully understand about mirrors as well as lenses, we could actually to start develop tools for us to obtain certain images. And so this is where we'll start the discussion of optical instruments. So there are multiple different types of optical instruments that I will try to discuss throughout this entire discussion. But one of the ideas for us to discuss first is how the eye really works. Because this is the sensor that allows us to see images. It is only for us humans. For all other beings also have eyes as well, but they work in something which is pretty different. But in here I will discuss about the human's physiology first. So for the eye, what you have is that you have your eyeball, and then in here you have something which you call as the iris. and then you have your lens here. So on this outside here is something which you call as the cornea, which is like the membrane between the outside world as well as your eye. And this lens here pretty much has a certain refractive index. And so this along with the muscles within your eyes, it allows you to adjust its focal length. And then lastly, you have this iris, in which it controls how much light that goes through. So if you want a much more sharper image, it will be much more closed, so that there won't be much spherical aberrations. But if you're within a dark room, your iris will open, so that there will be much more light that is going through your eye. And so this is why if you actually look at certain objects for different light levels, for bright light it's much more highly resolution, but then at the dark it's more like blurry, but you still can determine what the object is. So that's the idea. But I want to try to dive much more deeper into how do you discuss the eye. So the model is that we'll just call from here to here to be S prime, which is the notation that we obtained when we studied about convex lens. So if you have an image here, it will later be focused into this point, which is the focus point. So this is S prime and this is S, as long as you know what the focal length is. So the question is, at what focal length do I need to make the image to be very clear? So one way for you to actually to do this is that you need to make sure that the S prime will be straight away at the back of the eye. So it should go something like this. So that the focused light could be read by your retina, which is pretty much your light sensor. So let's just use this, and then we could actually just determine what's the focal length for a particular distance object, as long as you know what the S prime is, or the length of your eyeball, the diameter. So it's 1 over S plus 1 over S prime equals to 1 over F. So this is F equals to S prime over S plus S prime. So we could just divide everything by S prime. You could get S over S prime. No, sorry. It's S over S prime plus 1. So when your object goes very far, your focal length will turn out to be going towards S prime. So this is the way for me to draw the focal length in terms of the distance of the object, as long as you know what is the length of your eyeball. This is the length of your eyeball. It will be going something like this. You could see that there's the saturation point, so that if you have a certain object very far away, your eyes do not need to adjust it very much to see the depth. But this is different if you are looking at something very near. You need a much more change within your focal length in order to get the full resolution. And so this is where there is this idea of something which you call as the near point, in which it is where the normal eye couldn't really detect objects within 25 centimeters for normal humans. So its resolution isn't very clear if you have your object to be 25 centimeter from your eye. And so the eye pretty much works within this range, from your near point towards this saturation point of the S prime. So this is the focal length. So by the way, as a reminder, the focal length is pretty much, so if you have a higher focal length, it means that your eyes is much more sharp. It goes something much more like this. Compare that if you have, so this is high. Compare that if you have low focal length, which means, oh sorry, it's the other way around. So this is for small focal length, but this is for high focal length. And then obviously your eyes couldn't really create anything which is very sharp. Otherwise you might have a very sharp eye. So so this is why there's a limit at the bottom side here. So this is how the eye really works. But then we could also ask the question, maybe your eyes couldn't function very well. Instead there is some limitations in which your eyes could actually see. And so this is where you could study about nearsight as well as farsight eyes. So let's start with the nearsight. So so the way that we'll actually discuss about this is that we'll use the same idea. 1 over f equals to 1 over s plus 1 over s prime. But instead, what I will do is that I will try to make a function which is dependent on the s prime. So if we actually just draw this, something like this here, what we have is that if we actually do this, s over s prime over s plus s prime, this should equal to s prime over 1 plus s prime over s. And so for s primes, no, sorry. So for big objects, so when s is pretty far, is very big, compare that to s prime, what you could have is that this will later resolve in f equals to s prime. That's the saturation point. So it goes a curve something like this. This is if you have an object very far away. But then if you have any other object which is pretty close, it will be something like this. And so this is the length of your eye, which is the ideal point. But maybe your eye couldn't truly tell the difference from here to here, which is the ideal point for your eyes to actually to see. But instead it could be working from here to here, or maybe from here to here. And so this bottom one here is actually nearsight, because it can see near objects. So you could see here, so from the very bottom to the top, that's pretty near. But then for the top one, this is far sight. That means that you could only see something which is pretty far away. So for the near sight, what we could do is that we could just take a line here, and then we could try to observe what happens to very far objects, which is at this point. You could see at very far points, you would have the image to be before your length of eye. So this is the length of the eye, which means that the light will only focus until here. So when it reaches to the back of your retina, it is not fully focused. So that's why people who have nearsighted vision can't really tell any objects which is pretty far away. So how do you solve this problem? So this is where you put a lens at the front of your eyes. And so for nearsighted people, you just need to put a diverging lens, or pretty much anything which has a focal length which is negative. And so if we have far images, it will be refracted like this, which means that it will be something like this. So the rays actually appear as if that the object is much more closer. So this is what the nearsighted people would see after using the glass. It will be as if the object goes much more nearer towards their eye, so that they are able to know the object. But what about for farsight? So for farsight, if we also take the line, and then we see where's the object for near distance, it will be at this point here, which means that this is pretty much further than your eye, which means that for farsighted people, what they see is that the rays are going much more further than the retina, which also causes which also causes blurry vision for near objects. So the way that you could mitigate this is that you could just use a convex lens. So you could just make the image much more further. So it will be going like that. So it will be as if that it is going much more further. So this is the object that you'll see after wearing the lens. So pretty much what a lens does is that for people who has nearsighted or farsighted vision, they only move the image so that their normal eyes could see. No, sorry. So that their own eyes could see the image because of their own disabilities. So that's a very interesting thing to discuss when we're discussing about the eye. So after we have discussed about the eye, we could start to think about a much more prominent image sensor, which is artificial, which is called the camera. So how does the camera work? So pretty much if you have a focal length and then you are capturing image, it will later converge at one point, right? And so this is your focus. But unfortunately for a camera, you couldn't really adjust the focal length. This is fixed. So what you do instead is that you actually could change the place of your sensor. So this is movable. So that if you move the plate, or pretty much if you make the lens much more further, you could make it to be much more higher resolution. And so this is why if you actually adjust the resolution of a camera, you're pretty much extending or reducing the length of the barrel. So that's the idea. So now I want to talk about the magnifier as well as the microscope. So pretty much they work pretty similarly, but the main idea that I want to bring out first is the magnifying glass. So why do I want to discuss about the magnifying glass first? Because this is pretty much related when you are later going to be discussing about microscopes as well as telescopes. So for a magnifying glass, the idea is that if you have a very small object and then you observe it with your eye, there is a limit in where you could actually see the object. It's so this is about 25 centimeters, right? And the only resolution that you could get from your eye is within a certain solid angle, which I'll call that as alpha. But if you actually put a lens on it, the same height will later instead make it into a much more higher image. So pretty much if you put a lens in between your eye as well as the image, you are pretty much making the solid angle to be much more bigger because you're putting the lens there. And so this is like pretty much something like this. So the light ray in here and in here is pretty much the same. So I know that this description isn't really something that is intuitional, but if you understand why, it will later make much more sense. So anyways, so we will call something which we call as angular magnification to be the change of the solid angles, beta and alpha. So what's beta here? It's pretty much tangent beta, which is h over the length. So from here to here, we'll just call this as the focus. And why is that? So pretty much the way that I describe it is that if you have small images, the height doesn't really matter that much. So if you want to create a high focus, you could just put your image at the focal point, and then it will later be converged. So and the light will later be traveling in parallel, which means that you could see the object much more clearer. I know this discussion truly makes any sense. But anyways, so in order to look at the object instead, what you could do is that you could just put a lens, and then you could just see the object. And so where should you put the object? Sorry, where do you put the lens so that it will have a very big magnification? And a simple idea comes from the idea is coming from the idea when you put a object within the focal point, and then and so the image will and so the resulting image will be pretty much parallel. So this is pretty close to your focal length, and this will be your S prime, or the actual length technically, but oh well. So anyways, this will be the new height. But actually observing this from here, what I want to determine is the beta here, which is the solid angle. So if you increase the solid angle, you are pretty much observing much more smaller details. So this is what we want to use for magnifying glass. So for higher resolution or angular magnification, it's just beta over alpha. And so beta in here, this could be stated to be h over the focal length because it's pretty similar. And then you divide it by h over 25 centimeter, in which this is the limit that your eye could see. So the angular magnification is 25 centimeters over the focal length. That's your magnification. So unfortunately, just by using a magnifying glass isn't truly enough to enlarge the image. So there are more ways for you to actually to increase the size of the image. So one way of doing it is by adding another lens to increase the image, and then you increase the image again. So this is the idea of a microscope. So here's the idea. If you have this small object, let me just make the size much more bigger. So this will later be focused into a much more bigger image. So this will be the focal length because I wanted to have a very big increase of the size of the image. And then I could put another lens to see the resulting object from here. And this entire thing will be your length of the image. So, pretty much, let's actually determine what is the magnification for the objective lens, which is this one. So the magnification for the objective lens could be written in terms of the minus s prime over s, which we have already derived previously. So what we could do is that this would be pretty much, if we check this, the s prime here will be from here to here, or it's L minus f prime. That's negative. Sorry, it's L minus f prime. So f prime is your eyepiece, and then you divide it by the f, or the length from the objective lens. Sorry, from the object to the objective lens. And so if you have the length to be far greater than the eyepiece, this would be as if that it's L over f. So this is the magnification of the objective lens. But if you put the eyepiece to make the image much more bigger, the magnification is going to be 25 centimeters over this f prime. So the s prime is pretty similar, and that should be similar as well. So 25 centimeter is your near point, and then the f prime is pretty much the length from the focused image towards the lens again. So this is gonna increase the image much more, as we have already observed from the magnifying glass. So combining them both together, what we obtain is that the total magnification, And so pretty much angular magnification is pretty similar to magnification as long as the angle are very small. So this will be minus 25 centimeters, multiply this by L over F times F prime. And that's the magnification for a microscope. So for a microscope, you don't really change the focal length. Instead, what you could change is the length. And technically also your focal length. So if you want to observe much more greater objects, you could pretty much decrease your you could decrease the objective length, but then that means that you need to increase the length of your microscope. And so this is how the microscope works. You like pretty much change the length of your barrel, and then you adjust its height. So that's how microscopes work. But it is different if you actually compare this to a telescope. So a telescope takes a distant object which is very far, but it allows you to focus it on a particular point, and then you could determine some details about it. So the way that we'll describe it is by using the same idea. Maybe we could focus it at a certain point first. So this is from a far object. It will later converge at the focus point. From here to here, this should be your focus point. And then you could magnify the image much more with another focus of the eyepiece. So it goes something like this. So pretty much if you see the object literally from your point of view without any telescope, there is this angle which you call as the alpha. But after the magnification, it's going to be beta here. So let's determine what's the magnification. So we'll just use angular magnification here because it's much more easier. So the angular magnification for a telescope is going to be from the beta. It's going to be h over f prime, or the eyepiece, divide that by the h over f. So it's pretty much this angle here as well as alpha. So it's h here, which is the height, over the focal length. That's the tangent of alpha pretty much. And then there's the tangent of beta. So the magnification is gonna be f over f prime. So this is how telescopes work. The way that you actually magnify a telescope is by changing the lens, because you couldn't really change the length of the telescope, because even though if you have a long telescope, if you don't change the focal length, it doesn't magnify the image. So that's how telescopes work. But this only works for transmission telescopes. But there are some other types of telescopes which you call as reflective telescopes. So I won't fully discuss how those reflective telescopes really work. But the way that you could describe it is that if you have your telescope and then you put a concave lens, all of the parallel lights will later converge at the focal length. And then you could put a detector, you could put another mirror for you to reflect back to read, or maybe you could put it to the side and then read it from this side. Anything could work pretty much. So there are multiple different types of telescopes. And understanding geometrical optics allows you to create much more better telescopes. So that's pretty much all for today's discussion. So thank you very much for watching, and make sure to like and subscribe, and also please share this to your friend who really needs to understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.